I'm waiting. Okay. I think it's this one. Yeah, is everything okay?
Sí, te aviso cuando te queden, ¿qué son? 3 minutos, ¿sale?
Okay.
Dale.
So hello everyone, my name is Gibrán Morales. I am a student at Instituto de Astronomía UNAM, and my advisor is Nisim Freiha. Today I'm going to talk about neutrino propagation in winds around the central engine of short gamma ray bursts. Short gamma ray bursts are a subdivision of gamma ray bursts, which last less than typically last less than 2 seconds, and progenitors of these sources are the merger of two compact objects, either in black hole neutron star or neutron star configuration. In the first case, the associated magnetic field to this progenitor is only the magnetic field associated to the isolated neutron star, which typically is 10 to the 12 Gauss. But in the second case, several studies have shown that the magnetic field could be amplified up to 10 to the 16 Gauss. So during the formation of these short gamma ray bursts, several winds are produced, and these are produced these are produced to explain a cooling mechanism for the post-burst debris. There are two main proposed mechanisms. The first one is the neutrino-dominated accretion flows, which neutrinos of around 50 megaelectron volts are produced by Peirce annihilation within the accretion disks, increasing the neutrino density gradient, which drags and hits the surrounding baryonic medium into the so-called neutrino-driven winds. The disadvantage of the previous mechanism is that it results in an extremely inefficient process because it requires a large neutrino luminosity over short time scales. Those other mechanisms of energy extraction through magnetohydrodynamic processes have been proposed. In these magnetic processes, the toroidal magnetic field are forced to reconnect quickly and then twisted due to the differential rotation of the disk, hitting the surrounding medium and ejecting the wind outflow. In this case, a very intense magnetic field is needed to do that. So here at this point, we ask ourselves, do the winds really affect the neutrino propagation? Because every work performed until now has considered that neutrinos have a small cross-section and they are released in an isotropical way. And for that, the oscillation probabilities could be approximated to the vacuum case. So let's see in this work if this will work. We found that actually these winds affect the neutrino propagation, and we demonstrate that on this typical energy range, the mega electron volt range, neutrinos produced at these sources, they will oscillate resonantly. And that's because the neutrino potential, which is the physical parameter we require in order to compute the probabilities, is dependent on the medium density. And as I said before, these wind profiles were unknown until now, because several simulations have been shown that the winds, it is really, how can I say it? Like the density profiles of the winds are unknown until now, because several simulations have been performed to describe these density profiles. With these density profiles, we can obtain the neutrino potential associated with these profiles, mainly by these two mechanisms that I explained in the slide before. And these results were summarized by Murguia-Berthier in 2007, where she showed these two density profiles associated with these two mechanisms. Once we have these density profiles, we can compute and obtain the neutrino probabilities in all the cases. We know that there are 3 neutrino flavors, so there, we will expect 9 allowed transitions, which 6 of them are independent. In the case of the vacuum, the probability is only function of the neutrino energy, the oscillation length, the mixing angle, and the squared mass differences. But in the matter, we need to add an additional contribution associated with the density of the medium. So for that reason, it is important to know that it is important to know the density profiles that are associated with this mechanism. So in this slide, we present the survival probability of the neutrino electronic. Sorry. We present the survival probability of the electronic neutrino. And as we can see, there are resonant pattern effects in both cases. In comparison, if we consider that neutrinos are released isotropically, there will not be any angular distributions, and the plots would be simply vertical stripes. So it is worth mentioning that terrestrial detectors do not measure neutrino probabilities, but neutrino ratios instead, which are the amount of neutrinos of each flavor that they can detect. For that reason, once we know the probabilities, we can estimate these ratios with the conditions in both cases. So in this slide, we show the ratios for both cases, the magnetically driven winds and the neutrino-driven winds for a neutrino with energy of 15 megaelectron volts. In the continuous lines are shown the percentage of neutrinos expected. The red line is for electronic neutrinos, the purple is for muon neutrinos, and the blue one is for tau neutrinos. In comparison, we also show in dashed lines the expected neutrinos in the vacuum for electronic muon and electronic muon and tau neutrinos as well. So
3 minutes.
3 minutes? Okay. And as we can see, they differ from the vacuum case in both cases. They are not like similar in the vacuum case, but the most predominant effect is in the first one, the magnetically driven ones, where we have an additional contribution due to the medium. For example, if we are able to see an off-axis GRB with an angle of view of 10 degrees, and we, in our detectors, we detect a neutrino ratio of 0.38 in electronic neutrino, 0.31 in muon neutrino, and 0.31 in tau neutrino, that will indicate that neutrinos were propagating within a neutrino-driven wind scenario. This could lead us to indirectly determine which kind of progenitor would be associated with the source that produces that this kind of neutrinos. And yeah, that's all. Let's go to the conclusions. We derive the effective potential for neutrinos crossing the winds. With this effective neutrino potential, we can compute the resulting oscillation properties and compare them with the vacuum case in order to know if there will be any effect due to the winds. In particular, we found a stronger angular dependence on the expected neutrino ratios, and we can conclude that the joint analysis of this observable together with the short gamma ray burst ejected jet angle could lead to a compelling mechanism to discriminate between the involved merger according to the expected neutrino ratios. And yeah, that's all.
Thank you, Gibrán. If you have question, Fabio. Please, Fabio.
Yeah, so what about the intergalactic medium? Is completely negligible or can also contribute to the neutrino oscillations?
Yeah, the intergalactic medium could be approximated as the vacuum, since the neutrino cross-section is really small and they cannot affect the oscillations. So in order to compute the final probabilities, we need to do something called slab approximation, which requires the expected neutrino ratio that I presented in this work, and just we need to add the oscillations in the vacuum since the source to the Earth.
Which is the length scale for the oscillation of neutrinos in a vacuum? I mean, how long would you take? How long does it take for a neutrino to begin oscillating in parsecs or in megaparsecs?
Yeah, the oscillation, the typical oscillation length in this case is something between 10 to the 7 or 10 to the 9 centimeters, and this is dependent on the neutrino parameters that you choose to fit the neutrino oscillation length. So I didn't show in this presentation, but I actually in my work in progress I demonstrate that the oscillation length is typically smaller than the length scale of the wheels. So they in fact will oscillate resonantly.
Okay, thank you.
More questions? Because I have one. What's the accuracy or the precision that you could, or the person could measure this rate? Because I remember that was very similar, 0.32 and 0.36. It's not very similar to discriminate? Or,
Yeah, it could have some problems because they are like really close. But you need to know that in order to have like a better statistics, you need several detections. And for example, if you have like let's say something like 100 neutrinos, and you can like determine how many neutrinos of each flavor you are detecting, you will have a very more accuracy detection rate to this case. We expect that future neutrino detectors are sensitive enough to detect these neutrinos in this order of magnitude. And in a previous work, I showed that, for example, the hyperkamikande detector would have it, how can I say it? The hyperkamikande detector would have detect neutrinos from the event in with the gravitational wave in 1708-17, but if the source were more energetic, because this source was close enough to the Earth, but it was weak in energy.
Okay, thank you, Gibrán. William sent you, or sent for all of here, a link.
Yeah, it's a reference to a paper about neutrino oscillations in gamma bursts and energy deposition to avoid baryonic contamination.
Thank you, William. Then here we stop with the talks. That was the last one. I want to thank to all the speakers of today. And thank you very much for your presentation. And we can continue with the discussion. We skip the coffee break, and we can start with the discussion. If anyone want to share some point of view or want to ask something, this is the moment.
If nobody has a question, with Arnaud, we can come back on the data policy on SVOM if you want. Arnaud? Arnaud?
Oui, oui. Excuse-moi, comme j'avais pris un coup de téléphone avec Tatiana,